So in this video, we're going to look at the cosine rule for vectors. This is a super important tool in vectors and in linear algebra and higher math in general. It allows us to find the angle between two vectors. So suppose I have here a vector A and a vector B, and by convention, of course, we're assuming that they both start at the origin. And suppose I want to find the angle theta, that they make the acute angle theta in between these two vectors. So not this one, not the one like that goes this way, but the one in between, the acute angle, what you would think of when you say the angle in between the vectors. The key to doing this is two things. It's vector length. We're going to use our concept of subtraction of vectors, how we subtract vectors, the notion of vector length, which is determined by the dot product, and we're also going to use the cosine law. So from way back in high school. So if you're shaky on any of those things, please do go check out the videos on those, because we're going to assume that you know it in this one. Okay, so suppose I want to find the angle between these two vectors. Well, I'm going to remember what it means to subtract two vectors. If I subtract B from A, what is that? That's drawing B, placing the tail of B at the tip of A, and drawing B in the opposite direction. So B goes 2 down and 1, 2, 3, 4, 5 over. So from A, I'm going to go 2 down and 1, 2, 3, 4, 5 there. This is negative B, right, by our vector definition. And also we're going to be using stuff from our sort of basic concepts about vectors, what it means to have a negative vector and a vector sort of moving around, being the same vector no matter where it is in space. So if you're shaky on that as well, please go check out that video. So yeah, we take negative B, so the same vector B, and put it in the opposite direction. We put its tail at the tip of A and draw it in the opposite direction. So B's direction, its normal direction, is going out here, and so this is negative B going in the opposite direction. And then we start at the origin and we draw the line segment, or the vector connecting the origin to that point where we ended up. And that vector now has two things. It has a magnitude and a direction. I'm just going to get rid of this because it's a little bit easier to see. So this is the vector. This is, by definition, the vector A minus B. And of course, if we wanted to do B minus A, what would we do? It would be the same thing. It would be A goes 3 up and 2 over. So from the tip of B, we would go 2 over and 3 down, and it would be this. This is negative A. So we're subtracting A from B now. And you'll notice that, and maybe I'll do this in purple, you'll notice that connecting the origin to that point, this is B minus A. That is the negative of A minus B, right? Just like with real numbers, right? Negative A minus B is equal to, let me try to get the brackets in the right place, is equal to B minus A. So those vectors have the same magnitude, but just opposite directions. And so we're going to pick either one of them. It doesn't matter. We'll take A minus B because it's an orange, and I like that color a little bit more. No offense to purple, but I'm going to put this vector A minus B connecting now the tip of B to the tail, or to the tip of A. So I'm just going to erase all the rest of this because hopefully we can remember all the stuff that we just did. And if I place A minus B here, we can see that it bridges the gap. That the vector A minus B actually connects is the distance. Its magnitude is the distance between A and B, right? And this is again a thing just to review really quickly about vector multiplication or subtraction. If we have two vectors, right? If I have P and say Q, actually I think it's probably easier if I look at points P1 and P2. If I look at the vector P1 minus P2, right? This is the same as the vector or line segment connecting P2 to P1. So going from P2 to P1, right? If these are points, this is, and again, this is all in more detail in the videos on vectors and vector algebra, but the vector connecting going, so from, this says from P1 to P2, that's why we list P2 first, so it goes from P2 to P1, this is P1 minus P2, right? If I go in the opposite direction, I want to find the vector from P2, or I want to find P2 minus P1, this is going to be the vector connecting P1 to P2 in that order. So it's the negative. It's the same. It's the vector with the same magnitude, but just going in the opposite direction. This is P2 minus P1. So that's just what we're doing here. We're using that concept to say, okay, we know something about the magnitude of the vector connecting A to B. And why do we care about that? Well, because that is the third side of the triangle that these two vectors make. That is the third side of this triangle. And now that we know the sides of the triangle, we know something about the lengths of the triangle. Right? We know that, and again, if this seems at all strange, please do check out the video on it. We know that the length of a vector, A, is the square root of the dot product of A with itself. Right? Just like the absolute value of a real number r is the square root of r squared. We've generalized this, and now we have this idea of a norm, a vector norm, which tells us that the length of a vector is the square root of the dot product of the vector with itself. And that actually makes sense. It's not arbitrary. It actually makes geometric sense. And again, if it's at all shaky, please do check out the video. We go into a lot of detail on that. It's very important. So now I know that the sides of this triangle have length, magnitude of A, or norm of A, magnitude of B, or norm of B, and then the remaining one, its length is the magnitude of A minus B. And so this, of course, this one is, of course, the square root of A minus B dot product with A minus B. And this would, of course, work equally well if we used B minus A, right? Because when you take the dot product of A minus B and B, if you take the dot product of A minus B with itself and take the square root, right, you're going to get the same thing as if you take the dot product of B minus A and get the square root. And that should make sense, right? These vectors we saw have the same magnitude, and you can go ahead and check that if you have any doubts about it. It's a good thing to confirm. Okay, so now that we've filled in the sides of this triangle, now we can use the thing that I mentioned at the beginning, the law of cosines. Right? Now that we know all three sides of the triangle, I can bust out some of my analytic trigonometry, which of course I remember from grade 10 or whatever this is, and say, all right, I know that the law of cosines tells me the magnitude of A minus B squared is equal to the magnitude of A squared plus magnitude of B squared minus, there we go, 2 magnitude of A, magnitude of B times cosine of theta. And theta, of course, is that angle that we were looking for, the angle in between the two vectors. And so this is terrific. And actually, I should have put this in reverse order. I always do this when I teach it. I should have put this over here and said that this is equal to, because the order doesn't matter, this is equal to the magnitude of A minus B squared. And why do I want to do it that way? Just to make it a little bit cleaner, because then I'm going to bust out what is the actual definition of this. What is the magnitude of A minus B squared? Well, that is just because the magnitude of A minus B, right? Magnitude of A minus B is square root of A minus B dot product with A minus B. Well, if I square that, this is just going to be A minus B dot product with itself with A minus B. And as I think I mentioned in other videos, I hope I did, it's almost always easier to work with the square of a norm than it is to work with a norm, or with this magnitude function, this length function. It's just easier. You get to use the Pythagorean theorem. You get to use a ton of things. So when in doubt, try to square norms. Try to work with the square and see if you can figure out stuff that will then apply to the norm itself whenever you're doing proofs. That's a really useful tip. Okay, so So I have here, and let me color code this to keep everything straight. I have magnitude of a squared plus magnitude of b squared. Let me make this green, minus, and that'll be for b, so I'll make this b, and this will be a, and then I think I'm going to change theta to orange, just because orange is my least favorite of these colors, and I want to use it as little as possible. I like the pink and the green more. Okay. So now all I do is I just FOIL this out, right? What is this? This is a dot a. The dot product behaves very much like just multiplication of real numbers, right? There's a bunch of properties. It distributes. It's commutative. It's associative. All that stuff. So and again, if this seems a little bit weird, how am I doing all this stuff? Please do check out the video on dot products. I get a dot a minus b dot a minus a dot b plus now b dot b. And because, as I just mentioned, the dot product is commutative, the order doesn't matter. This is a dot a, I'll do a slightly nicer a dot a minus 2a dot b plus b dot b. But what is a dot a? Well, again, I saw that the magnitude of a is the square root of a dot a, which means that a dot a is equal to the magnitude of a squared. So this is actually magnitude of a squared, and I'll try to do a slightly nicer squared as well. I don't want people to get too confused. Magnitude of a squared minus 2a dot b plus magnitude of b squared. So, and I think you can see where I'm going with this probably by now. I have on both sides of this equal sign an a squared, a magnitude of a squared in the pink there, and then I have a magnitude of b squared in the green, and I'll just bring this down so that it's really clear. I want to put them side by side to make it really clear that these are equal, and we can cancel stuff. I'll just duplicate it so it doesn't bring the grid with me. Great. Okay. So I can cancel now, as I think you're probably anticipating here. I can cancel the a squareds, the magnitude of a squareds, and then I can cancel the magnitude of b squareds. And by the way, this thing that I'm doing where you slash in different directions, that's a just tiny little thing that it's really good to do on tests and assignments to show the graders to sort of draw their eye to the fact that this is canceled with that, that's canceled with that. Not essential, but never hurts. And so what are we left with? We're left with negative 2 magnitude of a magnitude of b cosine of theta is equal to negative 2a dot b. And of course we can now cancel the negative 2's, cancel the negative 2's, and end up with a b magnitude of a magnitude of b, and I'm missing a bar there, times cosine of theta is equal to a dot b. And there's two things. So now we can see how we're going to find the angle in between them, right? So cosine of theta is equal to a dot b over magnitude of a magnitude, I keep forgetting that bar, magnitude of a magnitude of b, and we can say, all right, so theta is equal to cosine inverse of a dot b over magnitude of a magnitude of b. I got the right number of bars there somehow. And this is the same thing as arc cos of a dot b over magnitude of a magnitude of b. Sorry, I'm struggling with this for some reason today. There we go, magnitude of b. That's gross, but you get the idea. I just wanted to put in both to sort of stress that these things are absolutely the same. They use them sort of interchangeably depending on which course you're in. Some people will say cosine inverse, some will say arc cos. It just depends on the prof, but or the teacher. I think this one happens more in university, the arc cos. But so there's a little subtlety here, right? Because whenever we invert a trig function, we need to make sure, that especially if we're plugging it into a calculator, that we keep in mind that we can get two values coming out, right? We can get two different distinct values, and the calculator will only give us one, and there could be another one that we're missing. There's little subtleties with that, so please, I'm not going to go into that in detail here because this video is getting kind of long already. But do go and check that out, the arc cos or the cosine inverse and the sine inverse videos, because it's important to have a deep understanding of that. But the point is, we're going to get the acute. We're looking for the acute angle in between the vectors, and so we can use the cosine inverse function or the arc cos function to get that. And if it's a nicely designed problem, then this will be a special angle, and so this will get an exact value. But the really important thing about this is actually a special case of it. Usually in math, a special case of a rule or a theorem or something, so some particular thing that you can apply it to, is much less important than the rule or theorem in general. Here we have the reverse of that. Here we have a general thing that we can do, a general rule, a general principle we can use, a way of finding an angle, and the fact that you can do this in general is much less important than a particular case of this, which is that this formula here, this can be used to tell when vectors are perpendicular, and why is that? Let's think about this. So if I have my vector, A and my vector B, and they're perpendicular to one another, so they make a right angle. Well, what is so the angle in between them? It's let me go back to the neutral color. This is pi over 2, and what is cosine of pi over 2? Well, it's 0. So this is telling me that if they're perpendicular, then their dot product is going to have to be 0, right? This is absolutely true. And so this is a really quick way to check if vectors are perpendicular to one another. I just take their dot product. This is also a way to construct perpendicular vectors. If I have a vector and I want to construct a vector that is perpendicular to it, I pick one that makes the dot product equal to 0. And this is super important. This idea of perpendicularity, it's extended in university to what we call orthogonality. And this just includes the case where we want to say that if A dot B are equal to 0, then the vectors are perpendicular. But what if one of them is a 0 vector, right? What if A is 0 or B is 0? Well, we're going to say, okay, if A dot B is equal to 0, then they're orthogonal. And orthogonal means orthogonality. This means that either they're perpendicular or one of them or both is the 0 vector. But this is the term for the dot product being 0. And this is just super important. If you take linear algebra, this is going to become ridiculously important. Then you're going to see things like the Gram-Schmidt process, and you're going to find out how important a concept this is. Same thing if you do some multivariable calculus. So this is, I want to stress, this is the really significant part of this. It's nice that we can find the acute angle in between any two vectors, and you should know how to do this. But the really significant thing is that we can test non-zero vectors for perpendicularity, for orthogonality. And I think that's it. I think that's a good place to leave this. I hope this was helpful. And again, like with all of these things, rather than doing a bunch of examples, it's great to do a bunch of examples. I would really suggest learning to derive this for yourself. I'd really suggest learning to work through this and be so, again, the test being that, can you explain this to someone? If you needed to explain this to somebody else, and you should be working in groups. Students should always be working in groups and explaining things to one another. Doing your own homework and submitting your own problems, of course. But if you have people in a study group who you want to show this to, if you can learn it well enough to explain it to somebody else, that's a great way to learn it for you and for them. And that's the real test that you understand it, is that you can actually derive the formula, and then doing the examples, being able to do particular examples will just become a triviality.